en Europa, en alguna parte, existe un póster que mi papá compró hace 30 años, 40 años, cuando mi papá existía todavía también, claro. Sí, sí, sí. Pero se ve súper parecido, yo creo que es por el norte de Italia, algo así.
Yeah.
Sí, pero podría ser acá.
Fernando está en San Francisco, parece.
Sí, no, Fernando.
Sí. No, esto, o sea, si alguien me dice eso es Chile, eso podría ser Chile perfectamente. Así que...
Claro, es el canal de Chacao.
Claro. Claro. Sí, con el futuro puente. Sí. No lo van a pintar de rojo, van a decir que son los copiones, digamos, pero sería bueno pintarlo de rojo. Ya está entrando gente, eso me parece muy bien.
Igual va a estar frío este fin de semana, van a haber 3 grados aquí en Temuco.
Chuta.
Está fresquito.
En Auburn hay como 6 grados.
No, aquí ya debe haber 15, 20.
No, en Auburn hay 6 grados.
Allá sí que hace frío.
Hi, Alice, can you hear us? We cannot hear you. Yeah.
Hola, buenos días, amigos.
Buenos días.
Hola, buenos días.
Buenos días.
Es las 8 aquí. Muy temprano.
Sí.
Qué pena hacer.
Sí.
Y Alice, ¿por qué hablas español?
Un poco. Estudio español en mi universidad, pero solo hablo español un nivel de la escuela primaria.
Pero ella...
Puedo leer mejor, pero entiendo y hablo un poco malo. En mi presentación, el PowerPoint es de español, pero hablaré en inglés. Sí.
Qué bien.
Muchas gracias.
Pero,
Genial.
pero Alice estuvo en Colombia un tiempo y también estuvo en Chile, en la Universidad Católica del Paraíso.
¿Ah, sí?
Sí, enseño para Católica del Paraíso. Es una profesora adjunct. Y también a veces trabajo en Colombia. Y este marzo estaba en Colombia con un Fulbright corto para la Universidad de La Sabana, cerca de Bogotá. Sí. I was supposed to be in Chile this year too, but the pandemic, I have tickets for Chile. I have tickets for me and my husband, but we couldn't use them. Yes, definitely.
I hope you can postpone them and come later, you know.
Yeah. It's with Delta. They're holding the tickets, so I can use them next year.
You know, you should see that the guys that are here, Fernando and Millaray, they live in Temuco. That's a very nice place. And Victor is in Valdivia. That's also very nice.
Yeah, I haven't been to Temuco or Valdivia. I want to visit both. I'm supposed to be at the conference, I think, next year in Temuco. So I'm looking forward to that. I've been to many places in Chile. Last year I went to Puerto Varas in Chiloé, but we flew to Puerto Montt, so I couldn't see the lands between. I've been to Atacama twice and other places. I haven't been to Patagonia. I want to go there. But when I visit, it's usually your winter, so it's not possible. Anyways, in the future, I'm sure it will happen.
In your winter, that's the best time.
Well, I know, but it's difficult with teaching. But yeah, I'm going to plan. I have a sabbatical in 2022. And I plan to spend part of the time, actually the majority of the time in Chile. So with Católica in Valparaiso, yeah. Yeah.
You have to visit Valdivia too.
Nice.
Yeah, I want to. I want to visit all of that region. I
Yeah.
think Chile is very diverse and very beautiful. I have never been anywhere I didn't like in Chile. I've liked, everywhere's different, but I've liked everywhere I visited. I went to Curacao once, though, in winter. It was so cold. I thought I would die, but it was still
Where was that?
Curacao.
Where was that?
Curacao.
Curicó. Oh, yeah.
Hi,
Curacao.
Alice.
Yeah.
Hey, Pablo.
How are you?
I'm good. I'm good. I'm
Good to
actually
see
in
you.
Florida right now.
Oh, great.
Yeah, a little break. I'm actually returning to Auburn right after this. Our graduation is tomorrow. And for
Oh,
whatever reasons, they're doing it in person outside in the stadium. And I have
oh,
a student who's PhD student to Hood. And so
I see.
I have to go do that. So we'll see how that works out.
Well,
But,
somebody have to work.
yeah. Siempre trabajo, sí.
Colegas, voy a dar inicio al EVIC solamente para comenzar la apertura. De ahí te doy el pase, Claudio, para que
Yeah.
presentes a Alice. Así
Thank
que
you.
voy
I'm going to start.
voy a compartir solamente para dar el inicio del EVIC. Ok, ¿se ve?
Sí.
Súper. Bueno, vamos a dar inicio a la versión, al EVIC 2020 del segundo día. ¿Ok? Solo como recordatorio que el EVIC es un evento anual que se realiza en Chile desde el año 2004 con el objetivo de promover la inteligencia computacional reuniendo distintas áreas tales como control inteligente, robótica, visión por computadora, neurociencia computacional, ciencia de datos, reconocimiento de patrones, Big Data, entre otros. ¿Okay? El EVIC, recordar que el EVIC está organizado por el capítulo chileno de la inteligencia computacional, ¿okay? Más una universidad anfitriona que este año corresponde a la Universidad de la Frontera en Temuco, el otro año también, así que paso el dato. ¿Ya? La inteligencia computacional en sí es un área de ingeniería que últimamente ha tenido un gran impacto en todo lo que son las áreas de conocimiento, ya que provee una gran cantidad de herramientas que permite automatizar información, crear sistemas capaces de tomar decisiones autónomas, etc. ¿Ya? Con lo que trae un gran impacto en la economía, en la vida de cada uno de nosotros y ofrece una gran cantidad de nuevos polos de desarrollo tanto para el país como para la región. ¿Okay? Este año la modalidad, bueno, va a ser por webinar, ¿ya? O seminario virtual, en la transmisión en línea con YouTube. Son 2 días este año con 7 exposiciones. Hoy día nos quedan las últimas 3. Y recordarles que cada presentación tendrá un moderador. ¿Ya? La primera presentación de hoy, que va a comenzar a las 11, con la profesora Alice Smith, ¿okay? Quien viene de la Universidad de Auburn. Okay. El moderador de la charla es el doctor Claudio Gel, de la Universidad de Chile. La segunda presentación del día de hoy es la que va a realizar el doctor Carlos Coelho, que viene del Instituto Politécnico Nacional de México. Okay. Y el moderador de esta charla es la doctora Doris Sáez, de la Universidad de Chile. Y la última charla del EVIC y del día de hoy es la que va a realizar el doctor Pablo Huise, de la Universidad Austral de Chile, en Valdivia. Ya quien va a presentar la charla de modelos probabilísticos profundos con aplicaciones en astronomía. La charla comienza a las 4 hasta las 5 y el moderador es el doctor Gonzalo Acuña, de la Universidad de Santiago de Chile. Algunas consideraciones para lo que es el seminario virtual. Las preguntas las pueden hacer utilizando tanto el chat de Zoom o el de YouTube. Tenemos un equipo que está dedicado a ver las preguntas, así que no hay problema en cualquiera de las dos plataformas. Obviamente manteniendo una buena conducta de comportamiento en el chat. Y todas las preguntas van a ser canalizadas al moderador, quien las va a realizar al expositor. ¿Ok? Sin más preámbulo, entonces le voy a dar el pase a a Claudio para que presente a Alice como corresponde.
Muchas gracias, Fernando. Bueno, estamos justo en la hora por lo visto, así que para mí es un honor presentar a la doctora Alice Smith, que viene de la Universidad de Auburn. Eso queda en Alabama, me dediqué a buscarlo, así que ¿dónde lo tengo aquí? Aquí está. ¿Lo ven? Sí, bueno, Auburn es este lugar aquí en Alabama, en el sur. Yo no sabía dónde quedaba, así que sirve para todos. Tiene un parque provincial, que es de donde vienen esas fotos tan lindas. Bueno, con esto de fondo, déjenme decirles que Alice Smith es Distinguished Professor del Departamento de Industrial Engineering, in Systems Engineering de la Universidad de Auburn, donde sirvió como chair del departamento entre el año 1999 y el año 2011. Además, tiene una posición en el Departamento de Computer Science y Software Engineering. El foco de investigación de la doctora Smith es análisis, modelación, optimización de sistemas complejos con énfasis en computación inspirada en sistemas naturales. Ella tiene una patente norteamericana, varias patentes nacionales, más de 200 papers. Recientemente ha sido editora de una revista de mujeres en ingeniería industrial y de sistemas, etcétera, etcétera. Ha trabajado con la NASA, con el Departamento de Defensa, con un montón de organizaciones del gobierno y empresas, tanto de Estados Unidos como internacionales. Tal vez una cosa interesante, ha trabajado en muchas partes del mundo y entre ellos ha estado ya en Chile con una fellow de la Fulbright en la Universidad Católica de Valparaíso. Para no alargarme más, dejo con ustedes a Alice. Gracias.
Thank you. That was a really nice introduction. I hope you guys can hear me well. I'm going to share my screen for my presentation. Yeah. Okay. Yeah, so I'm at Auburn University. I know many of you are students. So I would like to invite you to consider Auburn either for a degree or a research day. I've hosted many researchers, also your faculty from around the world and more recently from Latin America, in particular in Chile. So we have good ties. It's only one air flight from Santiago to Atlanta, which is very close to Auburn. So, and we have very nice graduate degrees, particularly our PhD degree. So yeah, and I'm also proud to be associate with IEEE, a fellow, a distinguished lecturer, and a current AdCom member, along with a lot of other work they keep asking me to do. So this talk I've chosen because I have been using evolutionary strategies for a number of years, but I find it's a technique on an approach and a paradigm that is less well known than many of the other meta-heuristics. And so I wanted to show how it can be used and its effectiveness. So my slides are in Spanish. Hablo un poco español, pero no es bueno. Entonces, hablo en inglés. So I'm learning Spanish. I'm actually now a degree-seeking undergraduate in Spanish at my university, so I'm very proud of that. But I prefer to speak in English, but my slides are in Spanish, and I find that's very effective because then everyone can understand at about the same level. Okay, so this is the overview of my talk. I want to allow enough time for questions and also not exceed my time. So I will move reasonably quickly, but you can always just ask me questions here, but also contact me by email later and I can share more information because I'm going to tell you a little bit about evolutionary strategies, just enough to give you a very basic understanding. And I'm going to be talking about 3 applications from my research. And I've chosen them because they're very diverse from each other, as you will see. Actually, this is a good theme for today because 2 of them involve multi-objective optimization, which this afternoon you will hear from one of the masters, Dr. Coelho. who is an expert in that. So one of the things that I like to keep as a theme for my research is to try to keep things simple, or as simple as they need to be. I found with computing readily available, and especially students and newer researchers, they get excited about all the different things they can add to algorithms and how complicated and how many subroutines and all of this extra stuff. And sometimes that's needed, and sometimes it's well motivated, but sometimes I don't think it really adds to the importance of the research. If you think about complicated approaches and complicated things, they tend to be very, very problem or application specific. They tend to be fairly brittle. In other words, if they are made to operate, if for problems or environments they're not designed, they tend not to do so well. However, if you think about simplicity, if you think about these things, I mean, I remember when I was actually a young student, one of my mathematics professors said, any of you could take a car, any car today that's on the market, and you could think of a better way to design it. You could find some small, at least small thing that would improve its design. But with a needle, you know what? How long has the needle been around? I don't know, prehistoric times. I mean, it's never going to be improved upon. So, you know, I'm not talking, what I'm going to show you are certainly a lot more complicated than a needle or a wheel. But it gives you the idea that simplicity has a lot of benefits and a lot of staying power. So these are 3 quotes regarding that. The first one is the well-known Occam's razor. If you haven't heard of that, you should have, because it's a very important saying in model building, and it comes from the Middle Ages. I'm not going to read either the Spanish or the Latin, because I don't even know Latin, although you can see it's not so far from Spanish. But basically it says to try to do things as simply as possible. And that's Occam's razor, which is try to make algorithmic and approaches simpler rather than more complicated. Albert Einstein in the last century said something similar also, to make things as simple as possible, but no more simple. So you have to get the job done, and that can add complexity, but don't add any more. My favorite quote is by George Box, who's a statistician. And what he said is, essentially all models are wrong, but some are useful. And this is the governing wisdom for my research. I know when we abstract real problems, and you'll see each one of these problems that I'm going to show you are all real problems. They're very specific. But when we abstract them in a mathematical and an algorithmic sense, they don't have true fidelity to the real problem. So in that sense, they're wrong. But I hope my research and the research that I'm involved with does have use and utility. So let's talk about evolutionary strategies, commonly abbreviated as ES or ASA in Espanol. This was developed back in the 1960s, actually in Berlin, in Germany. And it was developed basically at the same time genetic algorithms were being developed at University of Michigan by John Holland in the US, and a couple other, there were the Fogel, the Father Fogel out in California also developing some evolutionary approaches. But these were developed independently. You have to remember, way back in the 1960s, there was no internet. The exchange of ideas took much longer and was much more fragmented. And it was by Rechenberg and Schweifel. I've had the pleasure to meet Dr. Schweifel a number of times. And they're engineering background. So their background is not computer science, but in engineering. And they were trying to solve specific problems. And of course, as good German engineers, they were very technically oriented and also quite innovative and persistent. So they developed this approach based on the biological paradigm of evolution. And it's primarily, genetic algorithms are much more well known. And when I started working in meta-heuristics, the first paradigm I worked in was genetic algorithms, and I still love them, of course. But I found evolutionary strategies is different. A lot of people think, oh, it's just a variant, and that's really not true, because the main operator is mutation as opposed to recombination or crossover. The other thing is the selection is deterministic. In other words, every parent or every member of the population creates children or mutants. And they're really designed for continuous space. And the applications I'm going to show you are in continuous space. You can use them for discrete space, but that's not really where they shine. What I really like about this approach is there's very, very few parameters, at least in the basic version, which I mostly use the basic version, and I found it to be very, very effective. So what happens here? So this is the standard notation mu, which I don't like the notation because I work in probability and statistics too, and mu is always the population mean, but that's not what this is here. Mu here is the population size. Lambda is the number of mutants. So generally each parent produces multiple children, and usually quite a few. So it's more about the paradigm of, say, a fish laying eggs, or a frog where many, many children are created, but only a few will survive. There's two basic strategies. The original was the comma, which was more like biological evolution, where the children are pooled, and the parents always die, and then the best mu children are selected. The plus is more elitist and tends to be the one in practice, where you pool the parents and the children, and the best mu survive. So the main operator, as I said, is the mutation. And so the mutation is pretty simple. So what you have is a Gaussian, or a normal distribution about each parent with mean 0. So it's centered on the parent in hyperspace. And really the only parameter is the sigma, or the standard deviation of that normal distribution. So if the sigma is bigger, the children or mutants have a greater chance to be more different from the parent. If the sigma is very small, then the children are going to be very, very similar to the parent. And so this really works with this control of this sigma. And so what's more exciting about this paradigm is that they developed a rule that's both dynamic and adaptive to adapt the sigma automatically. So generally, when you pick parameters, you have to be very careful. What sigma is appropriate? Should I pick 1? Should I pick 2? Should I pick 14? But in this case, it doesn't really matter, because it's going to adapt. And it's something called the 1/5 success rule, which is based on how many children or mutants are better than their parents. And so it looks at the recent search history and makes a decision, should the sigma be made larger or smaller. And it's a very, very simple rule, but I've used it many times, and to me it's almost like magic, because I found it amazingly effective. You can do optional crossover. I typically don't do that because I like simple paradigms, and also it usually doesn't need it. And then of course you have to decide, this is generation by generation, so there has to be a termination criteria. So evolutionary strategies, as I said, are not so well known. One of my students did a Google Scholar over these 18, actually it was 17 and a half years, because this was done in mid 2018, and found about 1.3 million articles with genetic algorithms. And you can see that evolutionary strategies was, almost 2 orders of magnitude less than that. They're much less known, although it has been growing. The 2018 is just lower because it was only a partial year, but it's still very modest compared to genetic algorithms. So now I'm going to start the 3 case studies. The first one is in an area that I don't know very much about, but I worked with a student who was an aerospace engineer. And this is the work that we did together. And this is talking about the optimization of airplanes, of airfoil, which is basically the wing. It's and we're working on drones. Okay, so not a big airplane, but a drone. And this is specifying the geometry of the design of the airfoil, which apparently is a pretty complicated task. So what we're going to use are Bezier curves. And Bezier curves are defined by Bezier points. And this just gives you a little drawing of the typical airfoil where you're looking from above or below in 2 dimensions. And we're going to be working in 2 dimensions here, by the way. And you can see the Bezier curves. So the Bezier points are scattered around the airfoil. Let me see if I can get a pointer here. There we go. So these are the Bezier points. And in this case, they go in 1 dimension. And so the optimization, the traditional optimization to design these airfoils are to move the Bezier points in 1 dimension and look at the resulting airfoil design and then see its ability to fly. So this student's main insight is to actually allow 2-dimensional movement, where it can go not just in the original direction, but in the orthogonal direction as well, so in X and Y space. And so it permits a much wider representation of designs, which are potentially beneficial, and they actually are, as I will show you. But obviously the search space is much, much increased, which is a challenge. So what we ended up doing here is use a small population. And the reason we did that is the fitness was evaluated through basically a flight simulator. I'm going to tell you a little bit more about that in the next slide. But it was really computationally intensive to evaluate potential designs. So we have a strategy of 8 parents, each creating 5 children, and we're doing the plus strategy where they're pooled. We have the sigma, and every 50 evaluations, we check the 1/5 rule and modify the sigma accordingly. Here we're doing a bi-objective, and we're using epsilon dominance as the method to evaluate bi-objective, and where we're looking at lift and drag. So we want to maximize lift to get it off the ground and minimize drag so it can be most efficient when it's flying. And we terminate after a certain number of generations. So the encoding, we have 6 Bezier points. They're each encoded in X and Y. So we have a total of 24 values in real space as our encoding for each airfoil design. So this is the evaluation. We use a software called Xfoil. And as I said before, it's really computationally intensive, and it converts them into the XY coordinates into an airfoil and then determines its flyability. Again, to minimize, what we're looking for is to minimize the drag coefficient and maximize the lift coefficient. And they're both equally important. So Xfoil gives you an output like this, which shows you design and how they fly, and gives you some relevant statistics, which I don't know what any of them mean except the drift, the drag, and the lift. So these are some of our results. In this case, we did some standard work from the literature. We were comparing to a published source called D'Angelo, and that's that first listing there. So this is in our objective function space. So at the bottom is the drag. We want to minimize that. On the y-axis is lift. We want to maximize. So our ideal point is up here where my cursor is. And you can see our original seed. So we randomly started this thing. If we compare to the published work, which is the squares and the stars, as these are our Pareto fronts as the evolution went on. In other words, you can look from about 9 minutes to 3 hours. After 3 hours, we're getting this set of non-dominated solutions, which you can see, of course, are far better than what we started with naturally, but also better than what we were comparing in the literature. And they also span a lot of different spaces of the objective functions. So if a designer wanted to really maximize lift, didn't care so much about drag, there are good designs up there. And if the reverse is true, if it's more important to minimize drag, then there's a lot of designs there. So this was a really, and we did some other test problems too. I'm just showing you one because I don't have a lot of time. So this was really successful and promising. It worked really well. The ES seemed to perform very efficiently in the space and effectively. And the further work is to try to expand this from the airfoil to a fuselage, and also design other types of vehicles. Okay, something completely different. This is another research project, of course, with a different student. And this is about a facility location problem. So again, this is in real space, or real valued space, and we're doing it in the XY plane. And this is about semi-desirable facilities. So what's a semi-desirable facility? It's also called a semi-obnoxious facility. They're the same thing. So whether you want to look on the optimistic side of being desirable or the pessimistic side of being obnoxious, they've been called both in the literature. But what are they? They're things like airports, hospitals, recycling centers, police and fire stations. So population, people want to have close proximity to them. Because the services are needed, but they have a lot of potentially bad aspects such as noise, traffic, etc. And so they have this yin and this yang where you want to make them very close to people and population centers, but you also want to minimize what's called the social costs. So you have the transportation costs, which are the benefit costs, and then you have the social costs, which are the bad parts. And so you want to minimize both of those costs. The way we modeled it was also to consider that each of these facilities, we're going to place multiple facilities, has a capacity that can be exceeded, but then it costs a lot more to run it over capacity. And so there's a first cost for opening facilities and a cost, of course, ongoing cost for operation. So we have two cases. They're both real cases. The first is my city, Auburn, which is a relatively small city. And this is about the estaciones de bomberos. It sounds so much nicer in Spanish than fire stations in English. So what we do to solve these problems, this is done in the literature, is obviously people live kind of in a continuous way, but the population is transformed into points of demand based on the geography and also the density of where people live. So there's 33 points of demand. Right now we have 5 fire stations in Auburn. And you can see on the map, and we are doing this in XY space. The student that I worked with is from Mexico City. And so he also wanted to do something from his city, which of course, Mexico City is one of the largest cities in the world. And he wanted to look at transfers of solid waste. And in Mexico City, and that's in the bottom figure, there's over 7,000 points of demand, and there's just 12 of these stations. So we're going to look at both of these problems. The first one's obviously much smaller, and that was our original test problem. So this again is a bi-objective problem, as I mentioned earlier. We want to minimize the costs of operation, transportation, and construction. In other words, first costs of opening it. And that is our cost function up above. You can see it's discontinuous because once you add another facility, you have that first cost that bumps it up. So it's a piecewise linear function. You could model it as any function you want it. We did a piecewise linear. We also did a piecewise linear for the social cost, which is at the bottom. So if people are within a certain distance, so for example, an airport, so if you're within, 3 kilometers of an airport, it doesn't matter whether you're 1 kilometer away or 3 kilometers away, you're going to get all that noise and traffic, right? And then once you start getting in a more middle distance, and that's here, the bad social effects, social costs tend to decrease with distance. We modeled that linear. And then once you get beyond a certain thing, so if you're, say, more than 20 kilometers from an airport, maybe you don't have any bad social costs at all. You could be 20 kilometers or 50 kilometers, and the social cost is still essentially 0. But again, you could model these with any kind of functions. We chose piecewise linear. So this is characteristics of our evolutionary strategies. It's a little more complicated than the one I showed you with the airfoil. So what we did is we encoded these things with the XY coordinates of each facility. So again, we're doing it in 2D space. You could do 3D, but there didn't seem to be a point. And then we also, rather than have a single sigma for the population, we had individual sigmas for each member of the population, but also each dimension X and Y. We used a population of 10 parents, each creating 10 children. And we used a comma strategy just because it's worked better. And we were doing also recombination, which I don't have time to go, but it's basically a crossover similar to what you would have in genetic algorithms where 2 parents share information to create children. So how did we handle the multiple objectives? So this is one of the techniques that I published many years ago, and it simply rotates the objective function periodically, randomly. So it doesn't necessarily alter them. It's basically a binomial. You pick a p for each objectives. In this case, there's 2 objective functions, so it's p and 1 minus p. And you simply basically pull a random number each time and decide which objective. So it's super simple. You don't have to scale. You don't have to weight them, but it's very, very effective. So every 500 generations, we rotate an objective function. And of course, we kept our solutions just as in the previous case in a Pareto set. So we did 2,500 generations for the small problem and 25,000 for the one in Mexico City. So I have a little movie that's going to show you the one in Auburn. And what you're going to see is, again, that's that map. And we're going to be placing different fire stations. And you'll see them move around on the map. And this is over evolution. So on the left is the cost. In this case, this is the total cost on the y-axis. So we combine both the social cost and the operational transportation cost, and it's by generation, which is on the x-axis. So I've got to see if I can get this going. Sometimes I have this problem, so it's okay. I know how to fix this. So I come out of this. And I'm going to show you on this. Sorry, these movies can be a little fussy. Okay, so there we go. You can see it moving around the stations and of course improving the total cost over generations as it's placing these. Now we had two approaches to placement. One is where it's placing all of the facilities at the same time. However, that's not very realistic. If you think about the way a city grows, it's bit by bit, where typically you have one facility and then you add a second and a third. So we also did this in the same way as that, which is where, oh, now it comes up, sure. I'll show it again, just, and that's where you're placing them one by one. So you have a certain population, you place one or a few facilities, population grows, on changes, you place another facility and you do it incrementally. So we did both problems both ways, and I'm going to show you the results. This is the same movie. Okay. So this is the results of the bomberos. And what we have here on the y-axis is the social cost, and on the x-axis is the non-social cost, the operational and transportation cost. So the ideal points here at 0, 0. So what we have here is, this is the current solution way up here in Auburn. So if we take the current fire stations, this is where we're at in terms of both social cost and non-social cost. We did it, as I said, in two ways. The first one is the sequential, which is the more realistic, where I'm placing them one by one as the population grows. The second is where I place all of them at one time. And of course, I can do better because then I'm globally optimizing the current situation. But you can see each of them have a fairly nice Pareto set with a lot of different alternatives depending on the relative importance of social and non-social costs. And we also greatly improve on the actual situation. This is the results for the one in Mexico City. It's a much bigger problem. The graph's done in the same way. This is the current Mexico City solution. These few, there aren't so many when we place them incrementally, everything's here. And then these, if we place them all at once. But either way, you can see that the solutions that we found are much, much improved than the actual city planning solutions that are enacted. So the computational effort was certainly reasonable. If you look at the growth, it's pretty much linear and then evens out. And it did get a nice set of non-dominated solutions. This graphic is actually our solutions for the Mexico City one. You can see all the many thousands of demand points and then how we've placed our facilities. So the rotation of the objectives worked really well. The recombination, so we did have to add complexity to make this algorithm work well for this particular problem, and we added recombination, but we still use the simple 1/5 rule and everything else pretty much standard. Okay, last but not least, this again is a very different case. This is about order picking warehouses. So I have an active program in warehouse design and facility design. This is actually a photo of an actual Amazon warehouse. We did not do the work with Amazon, but the work we did was with actual data from a few different distribution centers and warehousing. And it's a really important problem. It seems kind of non-technical, especially after considering like aircraft design. You go to something that's a bunch of boxes in a room, but it's a really important problem, especially nowadays with worldwide logistics. And of course, the whole pandemic thing has pointed out the importance of being able to get goods around. And I don't know how much shopping you guys do online, but I do almost everything online except for groceries. So I just got done shopping for Christmas presents, and I will say 95% came from Amazon. So I'm happy. I'm helping Amazon get richer and richer and richer, which isn't my goal, but it makes it convenient and, of course, safe during the pandemic. So this is from 2016. You can see some of the financial impact. This is just in the US. And the thing we're going to be focusing on is what's called the picking cost. And that's where the person, so I go back to the picture. So these pickers, these people, you can see them with their little carts. They're going around getting the different items for each order and bringing them back to a central point, which we call the depot, where they're packaged and shipped out to the customer. So this is the most costly part because it's human-based. It takes time. They're walking around, they're picking things, and especially in developed countries, the labor costs are quite high. So it's about 55% of the whole operation. So these are two designs, one on the left and one on the right, basically what all warehouses look like. And you can see if you haven't been to a warehouse, you can think about it as like a library or even like a grocery store setup. So you have these long parallel aisles, which are called pick aisles. These are where everything's stored in these little bins in these locations. In the design on the right, so what have we added? We've added an aisle called a cross aisle. And this aisle is added for what purpose? It's added to make the walking distance shorter. So now instead of going all the way up and around, you can cross over. Of course, the bad part of that is you've taken space away from the storage. So you have this trade-off of how many aisles and where the aisles are, and also the storage. And this is what we're going to try to design. So what we will want to design, the layout with the location of the depot. We're also going to look at the aspect ratio of the rectangular area. And of course, how many cross aisles there are, how many pick aisles, what their angles are, and where they're located relative to each other. So one of the things that makes this really complicated is that these things, for example, let's go back to our picture here. These packages where these things are stored, they look random, but they're not random. They're not random. So a company is going to store things that are popular in a more convenient location where less walking is needed. And so where the products are depend on the design. And to evaluate the design, you have to know where the products are. So it becomes quite a complicated evaluation. And I'm not going to be able to go on all the details here. I actually have a whole hour seminar just on this project. And we're going to use evolutionary strategies. Of course, this is going to be a single objective. But we need to evaluate this with simulation. And what we're simulating are going to be the different routes of the order pickers, because every order is different. They're stochastic. They're not known with certainty. So, ¿por qué es un BHP? Okay, so BHP, so first I have to ask you what a BHP is. So if you're a student in computational intelligence, you should only be working on BHPs. And what is a BHP? A BHP is a bitch and hard problem. So if you're going to use computational intelligence, they are best, they shine most for bitch and hard problems. So why is it a bitch and hard problem? And of course, that doesn't translate well into Spanish. I'm sure it does, but I don't know any curse words. They don't teach us that in Spanish, so I can't translate it. Because again, you have to code all of the design parameters of the warehouse. How are we going to do this? Well, we do it in real space. I'm going to show you in a minute. That's why we're using evolutionary strategy. As I said, the products, where the products are, depend on the design, and the routing, which is how you evaluate design, depend on where the products are. And to route, so if you have a single depot, you're sending out a picker through the warehouse, and that picker, he or she, returns to the depot, and they have to visit each location where they're picking items from. It's a traveling salesman problem, TSP, which is NP hard, and we're going to be solving hundreds of thousands of those. None of them are really big. I mean, they're not like, you don't do 300 picks, you might do 30 picks, but we're going to be doing lots and lots and lots of them, and that's our simulation. So this is looks at how you're going to see the products laying out. So if you look at this graph, you'll see red, yellow, green, and blue. And these are the popularity of the products. So if a product's red, it's very popular, it's hot, it needs to be placed in a convenient place for picking. If it's yellow, it's not as popular. Green, much less popular. And the blues are the rarely ordered. And you can see in this case, they're in the periphery corners where to get to them takes a lot more walking distance, but they're not ordered as much. And of course, as I already mentioned, each order is regarded as stochastic, which necessitated a simulation approach. So how did we encode it? There's many different ways to encode it. This is what we chose. We chose to encode it in real space. So we're encoding these endpoints. These heavy lines are the cross aisles, and of course there could be different cross aisles. The thinner lines are the pick aisles. So each cross aisle has a beginning and an ending point. The pick aisles have an angle for each region. We also encode where the depot is, and we also encode the aspect ratio, equalizing the capacity of the warehouse. So it's all encoded in real space. We just normalize everything. You can see the distances. We start up here and just go around here and normalize over a unit rectangle in terms of those coordinates. And then you can see our angles here and so on. So this is the overall idea. We have order data, that we have sample order data. Here it shows select a warehouse design class. We actually originally started where we actually had different types of designs, and each would be a separate optimization. But we merged that. The ES was very powerful, so we could, now we just search over, as you'll see in a few minutes, a bunch of different designs using the evolutionary strategy, which uses this dynamic evaluator with simulation. So if a design is not very competitive, it doesn't seem good, we only simulate a few orders. If the design is very competitive, we want to evaluate it more precisely, so we simulate more orders and spend more computational time. And so the objective function is the average total distance traveled, which equates to time, which equates to cost. So we used, again, a small population of 5 parents, each producing 3 children. We used the plus strategy. We used a single sigma for the population using the 1/5 rule, which changed every 10 generations. We did not use crossover or recombination. I already talked about the second part. And then to route, we use the TSP, which we did with parallel and distributed computing to make it as efficient as possible. And of course, for each design, we have a subroutine which places the SKUs or the products within. So what I have next are 3 movies to show you. And let's see if they'll actually show. And what you're going to be seeing at the top will be the objective function on the y-axis, again, over evolution. And at the bottom, you'll see the design. So this is the best design found as it changes. you'll see the cross aisles, the pick aisles, and then how the product's laid out, which like the red, yellow, green, and blue I showed you before. We also will see the aspect ratio changed, and we'll see where the depot is, which is this little black mark. This is the smallest one we did. Let's see if I can. Okay. Let me get rid of that. Yeah, okay. Oh, all right, so let me show you here. So you can see we actually put in to start it a traditional design, and you can see this is automatically doing the designs. The ES is being wildly creative in the design, and there are actually some quite beautiful designs as it's searching to reduce the picking distance. Again, you can see this is equalized for capacity, so you can see the change in the aspect ratio. You can see where the depot is changing, where the product's layout is changing according to the design. And I think we're done here. This is the final design for this particular one. So yeah, there it goes. It takes, all right. Oops, there it goes again. All right. Well, so this is the output from our system. The original design we gave it is down at the bottom right. And then this is the one it developed. And you can see that overall, there was a cost reduction from the traditional design to the ES optimized design of about 4%, which may not sound like a lot, but remember that's 4% each and every day, you know, basically forever. So let me show you a couple more of these. This is a larger problem with more SKUs and more picks. Again, we gave it a traditional design to start, and it's creating some pretty funky designs, but they're operationally, at least by our modeling of it, effective. And you can see one of the common themes we found is this kind of spider web approach, where you've got kind of radiating out cross aisles, which is very interesting. And so I think this one's done. So in this case, what I think is really interesting about these designs too, if I were a human and I saw these aisle designs and I had to place the depot, I would place it down here, right? Because that's where all the aisles come together. But that's not the good place. The good place is actually up here. So to me, what we're creating are designs that are fairly counterintuitive, I think, to many humans. So again, we gave it that same traditional design. This is what it came up with in about 2%. And the last one I'm going to show you, this is the largest one I'm going to show you. Let's see if I can get it going. I don't know. All right, then I'll go back. The mysteries of PowerPoint. Okay, so this is the biggest one. It has these have skewed demands, and again, we gave it that same traditional one, and it's creating the designs. It almost looks like modern art to me, which I really like. Again, you can pay attention to how it's moving also the depot around as it's alternating designs. And we're reaching the final design here. There we go. So again, this saved almost 4% from the traditional design to the final. Again, to me, it's counterintuitive. The depot's down here, whereas I would have put it here, or maybe at least at where one of these cross aisles came to. This is our system. It's an interactive system. It's actually up on the web. We've made it open access. So it worked well. There's a lot of computational stuff that I couldn't go into that made it a real computational hog. But the ES was very effective. So one thing you might say is, well, these designs don't look very practical. And in some sense, there are some practical concerns that would have to be dealt with when you have acute angles. But this is an actual photo of a warehouse in the US. And you can see it's actually built with these designs in mind, where you have non-orthogonal aisling to reduce the picking cost. So those are my three applications. You can see they're quite different. And they were all used as the primary algorithm, evolutionary strategies. We didn't do a lot to the evolutionary strategies. Mostly it was just the plain vanilla or off the shelf. For multi-objective, it worked well. Single objective worked well. This is, so I mentioned that I was able to meet Dr. Schweifel a couple times, and he was given a retrospective interview in 2010 about his contributions to our field and where he thought evolutionary strategy would go. And he said something I think was really interesting, which is, I cannot forecast. Curiosity prevails in satisfaction. So again, I think these are really good guiding principles when we do research as you know, explorers, I can call us, where we want to be curious, we want to be excited and interested, and this ends up, you know, with frustration, but also ultimately satisfaction. So these are the references, and I'm happy to share my slides, by the way, with any of you. These are the papers that have been published so far. We've got some more coming out for that warehouse design one. This is a paper, if you're interested in multi-objective optimization with genetic algorithms. I wrote this with two of my former students some time ago, but it's been used by a lot of people. And if you're getting started, I recommend it. It's actually my paper with the most cites. And finally, I had the privilege to edit this book on women in industrial and systems engineering. It's 25 chapters of research from women-led investigative teams. It's really a beautiful book. And Chile is represented. We have 2 chapters from Chile. So I'm proud of that too. So you might want to check it out. And finally, I'm very sad I'm not there in person. This is me in Chile last year. Where am I? You guys should know, right? The Tatio geysers, which was one of the most amazing places I've ever been to. And Chile is a country of amazing places. So when I say this was extra amazing, it really means something. So that's my website and my email. I'm very responsive from email. So I look forward to hearing from you just now. I've allowed a few minutes for questions, but also afterwards, and hopefully in person in Chile next year. Thank you very much.
Thank you, Alice, for this wonderful presentation. I have some questions for you that have been sent to me by the team that is looking at the questions. The first question is, nowadays, deep neural networks are the trending tool that is used. How do you compare, or how does these approaches compare, or what are the advantages with compared to the deep neural network?
Well, actually, my dissertation, I graduated in 1991, was using neural networks. So that was my original research topic in computational intelligence, and I still use neural networks sometimes, although I have actually moved more over into meta-heuristics and evolutionary computation. So when I use neural networks, I use them more for modeling. So either classification, regression type modeling, prediction, compression of data, that type of thing. All of these problems are optimization problems. And so what we're looking at is optimal design, searching a space of design candidates and trying to identify in very large, complex, multidimensional space what are the design components and their parameters that yield the best outcome. So I think the tools are, I won't say mutually exclusive, because you could potentially use them together. For example, I've used neural networks as a function evaluator. So in other words, built a model of a stochastic system or complicated system of a neural network, and then used that as my function evaluator, because computationally it's very quick. But I think these are for different purposes. And so one of the things that you have to think about is not what tool do I have? So, you know, if you have a hammer, everything looks like a nail, right?
Yeah.
So, and that's one of the things I try to teach my students. I want them to be well-rounded, not just in computational approaches, but in the standard approaches and probability and statistics and standard optimization approaches, because often these things need to be put together in a modular fashion to have the best solutions.
Thank you. I have a few questions from viewers, from students. Here's one by Tomas Rojas. Is what kind of language do you use? He assumes Python is probably not efficient because it's an interpreted language.
So that's a good question. Generally, I mean, these things are all coded specifically for the purpose. I let my students generally code in what they want. I think these were probably all done in some version of C++ or C#. One of them might have been Java. I'm not really sure. Yeah, Python is a bit slower. Obviously, MATLAB's super slow. So generally for more advanced research, we prefer either Java, but although most of the students, at least in the US, versions of C are generally more popular than Java.
Okay. In one of your, in the second, no, the first of your examples with the drones, Andrea Valentina, that's one of the viewers in YouTube. She's asking, is there a way, you had a Pareto limit, right? But she's asking, is it a way to where you can identify a point where where both criteria are optimal?
Well, every point is where both criteria are optimal. So these are non-dominated points, are also called Pareto points. So to trade off one objective for the other, you have to get a decrease in the other. So in the sense, every point that I showed you on those curves is optimal. It's just a question of whether the designer or decision maker prefers one objective over the other objective. And that's something we leave to the human team to decide. We do not try to say this is the optimal point amongst these non-dominated points. And I think that has a lot of real world value because human designers can then bring in what they know. You know, what I said about every model being wrong, but some are useful. So there's always inconsistencies with this type of abstractions. They can bring those considerations in to arrive at a final design being guided by the output of these optimizers from the evolutionary strategy.
I have a question related with that. The number of parameters or the number of variables we're considering, is that something you decide? It's something your customer decides? It's something that is changing in time? I mean, you see a design that comes out and it's not what the users finds that it's not useful. So you look for different parameters to correct that difference in the solution. I don't know if
So I think you're asking about how do you model the problem?
Yes,
And
I mean,
honestly, that's an
yeah,
excellent question, because when I work with newer researchers, typically they want to get right into the solution methods. I'm going to use a genetic algorithm, or I'm going to use an ant colony. And I
Yeah.
tell them, no, we're not even going to talk about how to optimize it.
Yeah.
We're not even going to talk about that. We need to model it first. And to me, modeling it well, modeling it efficiently with an eye to the computation and also to the fidelity of the problem is the most important thing. And it's can be very difficult. It can take a long time. I mean, if you have a traveling salesman problem, that could be really easy to model, but these are more complicated. Like in the warehouse, we spent an awful long time and a lot of iterative work in trying to figure out how to effectively model that problem. And I think that that is really important. And then once we get a model, then we assess, okay, now how do we solve this model? So again, a lot of people want to put the solution technique first and then model it accordingly, but I don't think that's a recipe for success. I think you need to model it according to the problem. And you're absolutely right that a lot of times the modeling part needs to be done in conjunction with the domain experts. For example, in warehousing or in aerospace engineering. Is this a decent model? Well, you know, what's the pros and cons? What have we left out? And again, you know, what I'm showing you is the final work, but behind each of these are many months, and in some cases, like the warehouse case, many years of interactive work where we've started with something and it didn't work out so good and we've changed something else. So that's where a lot of the work is done, not as much often in the solution technique.
I saw in your, it seemed to me that you used all the time that there were the same amount of picking items for the warehouse problem, or that's not the case?
For each of the 3 cases I showed you, each case had a different amount, but
Yeah,
yes,
but
we kept
one.
the capacity the same for each instance. The design changed, but the capacity, because if you think about it from the warehouse perspective, from the company, they want to store a certain number of items. So they say, I need a warehouse that stores this. What is the best design? And so that's why you can't really compare designs that store different numbers of items, because then they're solving different problems.
Okay. I have another question by Maria Jose Briceño Niculin. Says, you mentioned in this presentation that in some point the objective function was rotated. Which is the purpose to do that?
Right. So that was with the second application. And that's because we had 2 objective functions. One was to minimize the social cost. One was to minimize the operational or transport cost. And so what we simply did is rotate those, because if you are operating with more than one objective, and again, you'll get the master of that this afternoon, there's a lot of different approaches. You can weight them. You can have one objective and bring the other into the constraint set. There's a lot of different approaches.
Yes.
But these approaches, some of them, they tend to have a couple problems. One is if you weight them or you make one an objective, the other constraint, it makes the optimization choose the relative importance of one versus the other. And oftentimes the human doesn't know until the solutions are presented. The other thing is you get scaling issues. So you can have scaling issues where one's in a very big scale and one's in a small scale. So numerically, it causes problems. So by rotating the objective function, you get rid of all of that. There's no scaling, there's no weighting. Computationally, it's extremely simple. And we found that it's tends to be very effective. I have never done it with more than 3 objectives. Typically, if I do multiple objectives, it's 2. So it might fall apart in high dimensional space. But for the type of, to me, more realistic, where you have 2 or 3 dimensions, it can work really well. And if they're interested, I can give them that paper was published in, I think, European Journal of Operational Research, and which covers that technique, and it has a lot of work that shows the effectiveness of it.
And I have another question about the problem of the warehouse. Did you try starting the evolution with a more complex configuration of the warehouse? For example, that the warehouse has a kind of spider web configuration at the beginning?
No, we didn't. For each of those, we started it with the standard warehouse. And the reason we did that is because we wanted to make sure the evolutionary strategy knew of the standard warehouse, and that if it was really the best solution, it would basically stay there. And so what we were saying is, we already know this is a good solution, and that's what people do in practice. Can we improve on that? And that's why we set the ES from that starting point. You know, theoretically, it probably wouldn't have made a lot of difference where we started the ES from, because again, there's a fair amount of randomness, and usually these techniques start with, quote, random solutions. But we didn't start with a random solution because we felt like a criticism could be, well, it never even looked at the standard one. And we didn't want that. So we're saying, no, we're going to start with the standard one and then see if it can improve upon it, which I usually don't do. Normally, when I work with these techniques and then the other two applications, we start with random solutions. We just randomly pick a set, generally of feasible solutions. But the warehouse, it was to kind of prove a point, I guess you'd say.
Okay. Different question is, what is the size of your databases, and do the results improve with more data? And that, also related to that, do you divide the data set in training, validation, test?
Okay, so I'm assuming that's probably talking about the warehouse, because we didn't really have data sets in the others. In the other ones, we had, problem instances. So, and that's a good question. So for the warehouse one, we had orders. Orders come in stochastically. Think about Amazon right now, okay? Every order is different, and they're not sure. I mean, they know some items are more popular and some are less, but they don't know somebody going to order one thing, 4 things. If they order 8 things, which particular things are going to be combined with each other. So what we did is we had real order data from some warehouses and distribution centers, and we would stochastically sample from that. So in that case, the more you sample just from probability, the more precise of an estimate you're going to get. And so the way that we handled that is that if a warehouse design was competitive, it looked promising, we would sample a lot to get a quite precise estimate of the average distance traveled. If a design seemed like a dog, no, I love dogs, but that's what we say, in the US, it's a dog, it wasn't very good. We would only sample a little bit. We'd say, okay, this is not going to be competitive. We're not going to waste more computational time. So I would say that certainly more data, is better, but you also have to balance that with some computational practicalities, because as you add sampling, you improve, but you're getting diminishing returns, and it really levels off. And that's what we looked at, that trade-off.
A more general question is there a limit for variables or parameters for such an algorithm, an ES algorithm?
Well, that's one of the fun things about our field in computational intelligence. There's really no rules, right? You can do whatever you want. That's why I like it. I don't like the standard techniques because there's all these rules and mathematics and forms you have to adhere to. Ours, you look at the world around us, our natural systems are amazing. The diversity, and if something works, it works. Look at that coronavirus. We wish it didn't work so well, but it works really, really well. And it popped up, and here it is. So I think, that creativity and being able to explore, and also being able to accept defeat, because a lot of things are dead ends and they don't turn out like you think, and it's discouraging, but you have to be resilient. I think all of these are important for researchers in our field, and I regard a lot of times it's kind of like a detective, where you're trying to figure out what will work, and you use the clues of your past experience, which may or may not lead you to the quote correct answers. But I'm also in awe of people who are really the thought masters of our field. When you think about, like I cited Reckenberg and Schweifel, I mean, I have not come up with anything original in that sense. I mean, I use what other people have done, and I hope I can contribute from an engineering perspective. But those are the people that are just amazing in their creativity and their diligence, and the ability to combine really rigorous technical stuff with this, you know, spark of from the outside, wherever it came from. And that's, I think, what all of us should seek, and not really be hung up by, you know, what can we do?
Yeah.
We can do what we want, and that's why we chose this field.
Do you have a couple of more minutes, or you want to?
Yeah. Yes.
Yeah.
It's
Okay.
my pleasure.
Thank you. One guy, he says, Claudio Yañez, he says he missed part of the presentation. He means the warehouse. And then he asks, which is true, the objective to minimize the travel times? I would say yes.
Average travel time, yes.
Yeah, but I would add there, do the people, the pickers, they are supposed not to know where the things are? Because if you believe that the pickers have some experience, then they will probably know where the 10 or 20 most asked things are, and then it's not good to move them around. Or if they want, for example, I don't know, a red paint, then probably the blue paint should be next to the red paint and not the other end of the, you know.
So those are perfect questions, and as I said, I actually have a continuing research in warehousing design. Actually, I'm working with a colleague and a company in Medellin, Colombia, on that. So yes, the answer is yes. So the pickers do know where things are, although a lot of times there's technology where they're picking to light. In other words, the storage lights up and it guides them. This is where I go, or it has a voice. It tells them where to go. So do you want to move around items in a warehouse a lot? And the answer is no. First of all, it's disruptive. You have to take the time to do that. And then, as you said, if the humans are used to it, then they have to readjust. So you don't want to be moving them around all the time, but you have to move around sometimes because products change. So your second question is, well, if I'm going to have the red paint, should I put the blue paint? So this has to do with product correlations. The work I showed you, we did not look at product correlations. The current work that I'm doing, it's actually with a distribution center for cosmetics, and we're looking at correlations. So if somebody's buying this eyeshadow, are they also buying the mascara? And then we would want to put them close together. So yes, there's a lot of nuances that can be added to make the warehouse problem more efficient, more like real life, but it also, of course, adds some complexity to the modeling and then thus the optimization.
And I have one other question is, you talked about social cost and non-social cost, but Francisco Miranda is asking, is there any one that is more important than the other? And what is the way to deal with that?
Well, I think that's a great question, and that's why we model it as two objectives, because we can't answer that. If you looked at the Pareto set that we developed, if you're a urban planner or a mayor or provincial governor, whoever's deciding, who thinks the social costs are most important, you can pick a solution on that extreme that would minimize the social costs, but it would increase the operational and transport cost. If you take a different approach, you can pick one on the other extreme. So we did not try to determine that because it's a complicated combination of you know, attitudes and abilities and government. And then when you get politics involved, we have to throw everything out the window, right? So instead, we just say, this is a set of excellent solutions. These are the trade-offs of each of the social versus non-social costs. And then they will have to make the decision. The algorithm does not presuppose that.
Okay, thank you.
You're
I believe
welcome.
there were some questions from the panel as well. I think Pablo wanted to ask a question.
Uh-oh, that'll be a hard one. Be nice to
No,
me,
no,
Pablo.
it's an easy one. It's an easy one. I'm sorry, I cannot avoid this question because you it's a not exactly technical. So I know you have been working on this book, Women in Engineering, and also recently there was a panel where you were one of the coordinators about women in engineering.
Mm-hmm.
So I would like if you can say a few words, because we have, of course, women students, but also to educate us, every people, every one of us about this gender and diversity. So could you say a few words? What can you do? Any recommendations? Because society is changing, especially in Chile. Probably is, I don't know, perhaps 10 years later than the US or something like that. So we have a very strong movement about 2 or 3 years ago. Maybe you know, because you have been coming to Chile almost every year. And also right now, well, because of the pandemic, it was stopped, but there is a very strong social movement also. I don't want you to enter into politics, but just to for you to know that for us, all these topics are very, very important.
So that's a good question. I actually gave a seminar course by Zoom a couple of weeks ago for Católica in Santiago. And I gave them some technical, but they also wanted me to talk about this book series. So I actually had a short presentation I made just for them. So this book is part of a series published by Springer. So if you're not familiar, Springer's one of the leading publishers in the world, especially for technical things. And they approached me, the series editor, wanting me to organize this book for industrial and systems engineering, which originally I said no, because I was too busy. But then I thought, you know, this is an important thing. And I know a lot of people around the world, a lot of women involved. So I said yes. And it turns out it's by far the longest. It has 500-600 pages in it. Book in the series, again, 25 chapters from around the world. Not every author is a woman, but I think there's like a total of 56, 58 authors, all but 2 or 3 are women, and all of the lead are women. So they're very diverse sets. What's also interesting about this book is that it includes the biographies of the women, but also included in the biography is how they got involved with the field and why they stayed with it. So I'm also editing. Currently, we're in the final stages of getting it together. Another book in the series, which is Women in Computational Intelligence. So that's, I think, going to be really important in our field. I think we have 19 chapters, 8 something, I don't know, close to 20 chapters. And I hope it will be published late next year. So I think we want to do it because the women-led investigative teams are actually doing amazing research, but we also want to have more visibility for women in these technical fields and to inspire the younger generation. And that's why the biographies are really important, that they could, you know, not be afraid to choose to be a technical person and to be, you know, a little bit of a minority in a field, that you can still have this most amazing career. So that's, and so I got involved with this, and I think for both men and women, the books can be really valuable, but especially I think for the younger generation of women, that was one of our primary goals, is to encourage them, which, you know, some of the feedback we've gotten so far has shown that that's definitely been the case. People have said, wow, they didn't know all this research was going on out there. So it's not to be exclusive, and it's not to say men can't do it. It's just to say women can do it too, and can be academic research leaders, even in these fields where women are a smaller percentage. And I don't think the US is 10 years ahead of Chile. I think actually, you know, we all have challenges. The percentage of women in the US in engineering is not that high, and it's remained flat for many, many years. It's not increasing.
Maybe we should be going to high schools or even elementary schools. Or
Definitely.
you. I mean, I surely do too, but I mean, it's probably should begin before, not in
Well, and that's why in these biographies of the women, we wanted for everyone to say, how did they get involved with engineering or computer science? Because I think that is really important to understand more about that. So thank you for asking, Pablo. Yeah, it was kind of a labor of love, and hopefully a year from now, hopefully when I'm in Temuco in person at the conference, we'll have the Women in Computational Intelligence book out.
Great.
And so fingers crossed.
Thank you.
I have one last question from a woman, Maria Jose Briceño. She asked, in the firefighter problem, how many iterations did you do before reaching the goal, the result?
Oh, so for the bomberos, we did 2,500 generations for that problem.
Yes.
And it was, I mean, computationally, it was done within a few minutes. I mean, it's a quick. And then for the Mexico City, as I said, we scaled it up to 25,000 generations, and that one took a couple hours. And we use a workstation. I mean, it's pretty high end, but it's nothing. It's not that fancy of a hardware.
Okay, thank you very much, Alice. It was great to have you here. Of course, it would be better if we would be together, but technology in this sense is fantastic. 10 years ago, this would have not been possible. So we thank you very much, and I hope to see you next year here. And
me too. Thank you again for the invitation. And those of you watching, don't hesitate to email me and let me know if you have any questions or you want to have further interactions. Thank you very much.
Thank you.
Adios, nos vemos.
Vemos.
Hasta pronto.
Adiós. Gracias.
Thank you. And I will now pass the word back to Fernando, who will talk about the evening session, afternoon session, I'm sorry. Yeah.
¿Aló? ¿Me escuchan? ¿Aló? ¿Se escucha?
Sí, se escucha.
Ok. Ok, bueno, quiero agradecer a Alice. Thank you very much, Alice. Una gran presentación. Hubo muchas preguntas, así que la gente se indica que los estudiantes estuvieron muy atentos. Básicamente lo que yo quiero es cerrar la sesión de la mañana para comentarles que tenemos 2 presentaciones en la tarde a partir de desde las 2:30 con el doctor Carlos Coelho desde México y a continuación con nuestro representante local, con el doctor Pablo Juice desde la Universidad Austral de Chile, Valdivia. Así que los espero en la tarde para estas 2 extraordinarias presentaciones. Y con eso damos por cerrado la presentación de la excelente presentación de Alice de la mañana. Así que nos vemos. Hasta luego.